Hello, we're back in the basement and it is very cold now because I'm not going to turn the heating on. But what I want to do is just address some of the points in a previous video talking about this antenna, not my video, one of Mark Steele's videos, where, take my mint out, where he says that the antenna in the Harvard Street furniture device is a microstrip antenna. So let's have a look at that. I've put a link to a website that lets you calculate and describes a microstrip antenna. So please have a look at that and look at some of the features and sizes of such an antenna. And particularly also some of the disadvantages of the microstrip antenna. So the claim is this, it's that the strip on here is it's clearly a strip. It's a strip of conductive material. It's mounted on this FR1 substrate, which is a printed circuit board. And the back here, as you can see, of the antenna is blank. There's nothing there on the back at all. You can just about, you can almost actually see the light shining through there, and you can see the strip at the back. So if I put some in there, look, you can see the shadow of that behind the antenna. But you can see the strip through the material, so you see there's nothing on the back, no more conductors, nothing at all. It's just a bit of translucent material that it's mounted to. And again, of course, the claim is that there's gain in direction of this side here, and that the material here blocks signal from going in the back of the antenna. Now, we've already experimented with this antenna and we've turned it back to front, and we've seen that actually the signal from the antenna is pretty much identical whether or not, depending which side is pointing towards the signal. It's the same whether it's this side or the other side, and we saw that on a previous video. We had a number of previous videos, including the one where I used a Lego turntable to rotate the antenna 360 degrees, and we saw that it's omnidirectional, so the gain and received or transmitted signal strength is the same in all directions. So let's just have a look at the anatomy of a strip antenna, microstrip antenna, or patch antenna, the same sort of thing. And again, you can see this in the link to the website, which will be in the description of this video. So, a strip or patch antenna has three main components. The first thing you have is you have a ground plane. So that be attached to ground with reference to the antenna. Then you have some sort of substrate or some sort of separator between the ground and the rest of the antenna. So this is the separator here. That could be, in the case of this antenna, could be some circuit boards. In the case of this antenna, the substrate is actually just air. So this one here, this is a patch antenna. See, there's just air between the patches at the front and the ground plane at the back. But you see, it has this ground at the back, this big metal lump, and then a space, and then the patches on the front. So we have our ground here, the metal ground. We have the space or the substrate, and then on top you have the antenna. And that then is sort of cabled to your transmitter via some coaxial cable, or in the case of the antenna we have here, it actually goes directly onto the transmitter circuit, which is just under this board here. So that's what a patch antenna looks like. You have the active element of the antenna, which in this case, with a Harvard antenna would be that strip. You have the substrate, the PCB, and you have the ground at the back. These need to be particularly sized, and you can see the formulas in the links in the description. And also I've put a link to a website where you can calculate the size of the antenna. On the website, you put your variables in, and it gives you the size. The important variables are the following ones. It is the frequency, taking my mint again, it's the frequency which you're running at, in this case is 869 megahertz. The second important variable is the distance between the active antenna element and the ground plane, so there, that distance there, and the third important variable in this antenna is the characteristics of this substrate here, and that also needs to be taken into account. The characteristics of the substrate, again, you can find the details of that in the link in the description. But for air, it would be about 1. So that figure there for the dielectric constant of this would be 1. So that's what a patch antenna looks like. The problem is, for this antenna here, this Harvard Electronics antenna, is that, as you can see, there's nothing on the back, so there is no ground plane. So that alone means that it is not a strip or a patch antenna, because there's no ground on the back. It doesn't exist. And Mark has said that, he said there's nothing on the back. The second issue is the sizing, and if you put the dielectric constant of that substrate, that FR1 circuit board, into the sizing calculator in the links in the description, and the frequency and the distance here, which is what, maybe 2.5 millimeters, the size that we have here just doesn't work. So according to that, that's the physics and the science of patch antennas, and the description of what a patch antenna is, that is not a patch or a microstrip antenna. So the other issues with these kinds of antennas is that they have some advantages in that they're small, they're low profile, and they have a usable radiation pattern which offers some directionality. The disadvantages are that they are very inefficient, and again you can see these disadvantages in the links in the description. They are inefficient, they only work at very low powers, and also they are low gain. So the claim that this is high power because of the large relay, or the 3.3 kilowatt rated relay, and that they're high gain, are actually not true. What's even more interesting is that the document that I referenced in the description is the exact same document that Mark has in his video. Yes, the diagrams are the same, and you can just get a glimpse of some of the text on his video on the document, and you see that text is the same. So the same document that Mark has in his video actually refutes the points he makes. He says it's high gain, it's a patch antenna, and he says it's high power. The very document he uses to try and prove what he says the opposite, which is curious. He obviously didn't read the document, otherwise he might not have used it. Now, just to make the point more evident, I thought I would build a 869 megahertz patch antenna, and here it is. So here is an 869 megahertz. Put a view of that patch antenna. So as you see, we have here the ground plane at the back. We have the active element at the front here, which is this bit here. And we have the spacing in between, the dielectric. In this case, the dielectric is air, and the dielectric constant is about 1. So I put the figures into the calculator. These are the sizes it gave, and I made this little microstrip patch antenna for 869 megahertz. But now we need to test it and see, is this patch antenna made for this frequency better than the Harvard antenna? Does it offer higher gain and more directionality? So this is a real patch antenna made using calculations and science and maths and engineering. So it should offer some gain and some directionality over and above the antenna that is on the Harvard device. So let's test that now. So I am receiving a signal here with this antenna here, which is the Harvard antenna. So let's have a look, shall we, at what that signal strength is right now, and we will compare it to the patch antenna. I'll just make sure all the connections are properly connected and everything's good. Make sure we get a sensible reading. There we are. So I've oriented the antenna here so that the patch, the strip on the antenna, is facing towards the transmitter. The transmitter is just over here. There we are. It hasn't moved at all since any of the previous experiments. It's there. So we're going to do a test now and see what the signal is like with these two antennas. So let's have a look first at the Harvard antenna, which is still plugged in. Assuming there. So that is the signal we are receiving from the transmitter. It is at 869 megahertz. If I just put the cursor here, we'll be able to get some details. Okay, so we have negative 29.5-ish dB up to about neg 30-ish, say neg 29.5, which is about what we had in the previous experiments as well. So now I will detach that antenna and I'll attach the antenna that I've made. So remember this, look, it's neg 30 is a bit lower. We'll give it the benefit of the doubt and we'll say it's minus 29.5 decibels on the signal here. So I'll zoom out now here and I will show that I'm going to detach the antenna here. And I'll attach the cable to the spectrum analyzer to the patch antenna here, the Microstrip patch antenna. Bam, that's it up there, there we are. Okay. And the signal we have now is minus 25.9. So we've gone from about minus 26. So we've gone from neg 29.5, we said, to about neg 26.2. So that's sort of 3.4-ish decibels gain. So that's 3 dB better performance with this antenna than the one that ARC still says is a patch antenna. Let's now look at the what's called the front to back ratio. So how much energy comes out of the back of the antenna on our test rig here. We've seen in the videos of the Harvard antenna, particularly the really easy response that I made to Mark, but you can turn the Harvard antenna back to front and the signal is pretty much identical. So the claim that the substrate on which the antenna is built, the green thing there, blocks the signal at the back, it is completely untrue because it doesn't, because you can turn it around and the signal is the same. But we need to make sure we can prove that for this antenna, so let's do that now. How am I going to turn this thing around? It's going to be quite tricky, isn't it? But I'll turn it around and we'll see what the result is. So remember, at the moment we have sort of neg 26-ish, neg 25 point something dB. That should change significantly. Let's just check that again. So neg 26 dB, let's call it neg 26. Okay, and that should go down when we turn it around. Quite how I'll turn it around and keep all this, I'm not quite sure, but we'll work it out. There we go. So, I'll turn it around so it is like that. Stay there, I might just put some there to keep that there. What do I have? Attach to things. There we are. If I just stick this on the cable at the back just to keep it from falling over, that should be okay. There we are. And the received signal now is minus, let's say minus 40. So that's quite a big decrease in signal between the front and the back of the antenna. I'll turn it around again now to point towards the other antenna in the test setup here, and we'll see what the difference is. Again, there we are. minus 25.9. So there we are. I mean, what can you say? It's pretty clear from these very simple demonstrations that actually the antenna on the Harvard device is not a patch antenna, even according to Mark Steele's own document that he has in his video, and that the characteristics and performance of the antenna that Mark claims is a patch antenna is so completely different to the performance of an actual patch antenna, which you can calculate for yourselves on the website, that it's pretty clear and very conclusive that Mark is talking complete and utter crap. What more can you say? That's about it, really. Thanks for watching and have a super day. If you have any questions about antenna theory or the science behind this, then please ask in a comment below, or I'd point you towards Andrew McNeil's excellent antenna YouTube channel, where he looks at various antennas in various guises, and you can get a lot of this information from his channel as well, just by watching his really good videos. And in fact, he made a video on this very antenna, the Mark Steele Harvard engineering antenna, which I will put a link in below in the description. Please subscribe to, I don't care, subscribe to me, I'm not a YouTuber really, but subscribe to Andrew McNeil because he does some really good fun stuff, if that's the kind of thing you're into. Thanks for watching, and have a good rest of your day, or night, whenever I get to upload this. So as a quick addendum to that last video about the patch antennas, I thought I'd just include Mark's claims and some of the documents that I spoke about in the video. So here's Mark. He's talking about this Harvard antenna. I'll zoom in a little bit so you can see that. See, it's the right video. And there's a couple of particular bits which I'll draw your attention to, which are worth looking at. Here we go. So this is his little preamble.
Because obviously we've had a number of crazies.
I'll tell you.
Who unfortunately think this is an omnidirectional antenna. In fact, there's some crackerjack who's done a video. Well, she needs to get some new equipment, and he needs to understand what he's talking about.
Now, I'm not sure if the crackerjack is me or Andrew McNeil. Either way, we both have done a video. Andrew explained with great technical depth the details of this antenna, and I made a video doing a demonstration, an actual demonstration, in fact quite a few now, showing that the radiation pattern of that antenna is omnidirectional. So that's interesting. So we get Mark's claims against actual empirical data and experiments, and the claims of an actual antenna expert who has a YouTube channel full of antenna videos. So that's interesting. Let's continue.
Now, you see this microstrip. That copper strip there is an antenna, all right?
So he said it's a microstrip. Let's just continue. So that's his claim. It's a microstrip. Let's listen to what he says about the back of it.
And you'll see it's not on the rear. Right? There's nothing there's nothing on the back side of this. All right? Nothing.
There's nothing on the back side of it. Nothing.
The radiation pattern cannot get through there. Can't get through. All right?
If there's nothing on the back of it, why can't it get through? What stops it? You can see as we saw in the antenna here, the little strip of the circuit board strip here behind the antenna there. You might be able to see it very clearly on the video here, but you can see the shadow of it where it blocks the light coming through. So that substrate, that material, doesn't block light, but does block 869 megahertz. That doesn't quite make sense, but let's continue a bit.
So this is a directional microstrip antenna. All right, you see that? So that's what it is. It's directional. See that little bit of material on the end there, that little dielectric pattern on the end.
So it's a directional microstrip antenna. He has a particular document that he uses to try and support his claims. There it is there. So there's the document that he uses to try and support his claims. I found the document on the original website. Let's have a look at it. So that is the original document. So it says radiation patterns of patch or microstrip antennae. There's elevation azimuth planes. Radiation patterns, blah, 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 azimuth elevation plane. So it's the same document. It's the same website here. Let's see what it says about microstrip antennas. I will just zoom in a bit so we can see it all nice and clearly. Again, this is in the link in the description below. I'll just pull the camera up, zoom in there. Hope you can read that okay. Excuse me. Definition. So let's start at the top. Microstrip or patch antenna. Start at the top. Definition. An antenna formed by etching out a patch of conductive material, that's a strip, on a dielectric surface, that is the circuit board with green thing that it's on, known as a patch antenna. The dielectric material is mounted on a ground plane. The dielectric material is mounted on a ground plane where the ground plane supports the whole structure. Okay, so there should be a ground plane. Let's look at a diagram of this. So here we are, here's a diagram. So we have here the patch. Notice it's not just a line, it's a patch of material. This is the substrate here, that is the green circuit board. Behind it is this big ground plane. The ground plane is, again, conductive material. But as Mark said, there's nothing on the back, so there's no ground plane. And this is the structure of a microstrip antenna from the same website that he uses in his video to support his claims. But actually, it completely denies what he says. Also, look at the dimensions here. There is a length and width of the patch, and there's a height here, which is the thickness of the substrate. And we can do some calculations to work out what those sizes should be. And we'll do that in just a minute when we've looked at this website a bit more. So there we are. A actual micro patch antenna needs to have the active element, the patch, which is not just a straight line, a substrate, and a ground plane. Marcus said there's no ground plane on his antenna. There is nothing on the back. It is therefore, by the definition of the very document he cites, not a patch antenna and not a microstrip antenna. Down here as well we have, so these are the radiation patterns he has in the document on his video. These are some characteristics. The ground plane there, so there must be a ground plane again. But interesting, down here at the bottom we have some disadvantages. So advantages, it's quite small and less bulky, that's true. That's why they often feature in phones. Easy to make, yeah, a bit of circuit boards, less volume, and it's not very high, it's quite low profile. So it's quite a nice antenna if you have the right application for it. But the advantage is, the antenna efficiency is low. It's not a very efficient antenna, it's not very good. They exhibit low power handling ability, low gain, narrow bandwidth. So he says in his video it's a high gain patch antenna, but again the very document that he cites to support what he says that these antennas are low gain. They're also low power handling. They don't handle much power. And the reason why they don't handle much power is because you've got quite a small space between the active element, which will have the power applied to it, and the ground here, and there's a little dielectric here. That dielectric has to withstand all that power, and the risk is you get arcing and sparks between the two surfaces here if you have too much power. But he says that the Harvard devices on street lamps are high power. So these are low efficiency antennas, low power handling ability, low gain, whereas Mark says that they are high gain and they handle high power, and that it's a microstrip, which it clearly is not. Let's look now at the calculations for microstrip. This is the calculations I used for the one I've made here. So the dielectric content I put as 0.95, it's air, and that was a sort of rough guess, but you can change that and the actual dimensions don't change all that much. The dielectric height, which is a height between the ground plane that Mark hasn't got and the active element here, is 30 millimeters, that's 3 centimeters. and the frequency is 869 megahertz. Zoom in a bit there so we can all see it nice and clearly. Dielectric constant 0.95. The height is 30 millimeters, and the frequency is 869 megahertz. It's gigahertz there, but we chose megahertz from here. There we are, megahertz. And we calculate, see the width is 174 millimeters. That's the width here. And that's the width of the active element here, 174 millimeters, and the height is 135 millimeters. And that's the height of the antenna I made here. And that's the height that we have on the website here to calculate the size of a patch antenna, which you can do yourself. It's everythingrf.com. Again, I'll put this in the description of links below. The antenna that Mark has, as you see, it is clearly very, very different. The sizes are not the same, and you can see, because shine a light through it, there is nothing on the back. See, the light shines right through it. And if I turn it round, and you can see the oh, it's not very good, is it? There, there we are. If I just shine there, you can see the shadow of the copper track behind there, and you can see the shadow because there's nothing on the back. There is no ground plane. So there we are, just to summarise Mark's document that he cites in his video, trying to refute my video, actually completely negates everything he says about a patch antenna. There we are. I mean, it's really funny. It's crazy. I don't understand. Yeah, okay.